Hello everyone, my name is Joshua Peeples. I'm a fifth-year PhD candidate in the Department of Electrical and Computer Engineering at the University of Florida, and I'll be presenting to you all today about the Learnable Adaptive Cosine Estimator, LACE, for image classification. Feature embedding models have been successfully used in several different applications, particularly for image classification. State-of-the-art classification networks typically use softmax loss. And in the literature, it's been shown that these models produce these angular feature distributions as shown here on the right, where each color represents a different class. And we also observe here that each class lies along a unique principal vector. As currently constructed, the softmax plus cross entropy loss functions have no inherent property to consider the intra-class and inter-class relationships that are present within our data. To improve the discriminative power of the features that we're learning, as well as to use the angular information that's present within our data, we propose the Learnable Adaptive Cosine Estimator. Our method takes inspiration from the Adaptive Cosine Estimator ACE approach coupled with cross-entropy loss. LACE is integrated into a deep learning framework by using the convolutional neural network backbone to extract a high-dimensional feature vector representation. Our approach then applies data whitening, a powerful transformation used to normalize the data. And for our work, we have samples that belong to a certain class, referred to as a target class, and then samples that do not belong to this class, we refer to this as background information. We also have a new test point or test sample that belongs to the class of interest, and then we also have a target or class signature, which is the representative of samples belonging to our target class. To begin the data whitening operation, we use the background mean to center the data so that the background samples are shifted towards zero mean, and then we use the inverse covariance to rotate and scale the data such that the background samples have a spherical distribution. Through this data whitening approach, we're able to improve the cosine similarity between the target signature and the test sample. Here we have our overall objective function, which is computing the cross entropy loss in this whitened data space, and ideally we want to maximize the cosine similarity between the correct target signature and a given sample. An advantage of our approach is that we are able to estimate the background statistics of the background mean and background covariance and target signatures via backpropagation, as opposed to previous approaches where you need to set this information a priori. We compared our approach with the softmax loss as well as angular softmax alternatives and other feature regularization approaches, and through both quantitative and qualitative results as shown here, we're able to achieve comparable or better test accuracy performance, as well as improve the intra-class compactness and inter-class separability of our data. To summarize, we have three major contributions of our work. We were able to improve the discriminative power of the features that we were learning through this data whitening operation. Also, we were able to learn the target signature as well as the background statistics via backpropagation. And also, our approach has the advantage of not needing to set hyperparameters such as angular, scale, and margin as previous approaches such as cosine face, arc face, and sphere face. Also encourage everyone to check our paper and code, which are available here through the URL or also through the QR code. Thank you for listening to our presentation. Please feel free to contact me if you have any questions.